This video goes along with a series of videos where I described how to do the integration process and then now looking at indefinite integral examples. I put a link to all of the earlier videos in the description of this one, but let's go ahead and get started on the examples I have planned out for this particular video. Now, I've written up the indefinite integral rules for a lot of different cases off to the side, and we're working with just the very introductory ones that aren't looking at going backwards on the chain rule. Just those types of problems that are very basic definite integrals and how we go backwards on the differentiation process. Let's get started. So now looking at this first one, it's the integral of this 3 minus 4t to the first power, always look to see if there's an exponent on the parentheses, times t to the third dt. We don't have anything in our integration process that allows us to go backwards on products of functions specifically. There will be u substitutions in case what that other factor is the derivative of what's being acted on. And then later on there's like this pseudo one with something called integration by parts. But for now, if there's a multiplication of functions and it didn't come directly from taking the derivative of a specific item, then I have to do that product to get ready to do integration. So here I'm going to go ahead and distribute this t to the third through each term in the binomial. So now I have 3t cubed minus 4t to the fourth as my integrand, and I just rewrote the integrand. I haven't integrated yet, so I still have to bring down the integral sign and what variable we're integrating with respect to. Now that I have it as term by term, I have a property that says if I'm taking the integral of the addition or subtraction of two functions, I can integrate each term separately. And also, if I'm integrating a constant times a function, I can pull the constant out in front of the integral and multiply that to the integral of the function. So next, in each of these two different terms, and remember I don't have anything other than just one on the outside exponent, I'm going to write this as 3 times the integral of t cubed dt, and then minus 4 times the integral of t to the fourth dt, applying those two rules. So now we're going to look at integration. With respect to the letter t, I have t to a number power. So when I have a letter base to a number power that I'm integrating, as long as that power is not -1, throughout the integration, I add 1 to the exponent and divide by that. So here, adding 1 to 3, so keep your base t, add 1 to 3, that's 4, and divide by 4. So I already had that coefficient of 3 out there, and I'm dividing by 4. Then minus, keep your base of t, same sort of scenario here, add 1 to 4, that's 5, divide by 5, I have 4/5, and then to add your constant term c. Okay, let's do the next one. Here it is the same sort of situation between them. I just have to remember what is the exponent notation when I have a radical notation. Well, remember the exponent notation has your base of x, the root of the index is the denominator of the fractional exponent, and the power is the numerator of your fractional exponent. And then that's times x plus 4, quantity dx. My exponent here is 1. If it were any other number, I would have to carry that out first. And then remember when we multiply exponential expressions that have the same base, we keep the base and we add the exponents. So this is the integral of multiplying x to the 2/3 times x to the first. You keep the base x and you add 2/3 plus 1. Well, 2/3 plus 1 is 5/3. So this is x to the 5/3, and then plus, this is 4x to the 2/3, and dx. So again, I just rewrote the integrand to get ready to integrate. I haven't integrated yet, so that's why I still have to bring down the integral and the telling us what variable we're differentiating with respect to. Okay, now letter base to number power, and the power is not -1. So to integrate that, we keep the base, we add 1 to the exponent. 5/3 plus 1 is 5/3 plus 3/3, which is 8/3. And then divide by 8/3. Well, divide by 8/3 is multiplying by 3/8. And then plus, I have my coefficient of 4, and that's going to multiply by, keep the base x, add 1 to 2/3, that's 5/3. And when I divide by 5/3, I'm multiplying by 3/5. And then that's plus c. And then right here, 4 times 3/5. Think of that as 4/1 times 3/5. And in multiplication, you multiply straight across the top and straight across the bottom. So 4 times 3 is 12 over 1 times 5 is 5. So that's 12/5. And I'm just going to erase this and write that here. And then we remembered our plus c. Okay, how about the next one? Well, the next one is a division of something that has a variable, and I don't have any rules for integrating if there's a division of functions either. So now what I need to do is I need to rewrite this somehow so it conforms to one of those types of indefinite integrals I have a rule for. Well, 1 minus sine squared x, if you remember from your 8 fundamental trig identities, we have one that says cosine squared x plus sine squared x is equal to 1. So if I subtract sine squared x from both sides, I get that cosine squared x is equal to 1 minus sine squared x. So this 1 minus sine squared x, I can replace a cosine squared x in its spot. And also this number factor of 5 in the denominator, it's times that entire denominator. So I can bring that out front, but remember it's in the denominator. So it's going to come out front as a 1/5 times the integral sine x over cosine squared x dx. So sometimes you will have to use your trig identities with some of these. Now this cosine squared x in the denominator, still this is not something I can integrate in the form that I have. But when I look at the integrals of the trig functions over here, I see that I do have something that I can actually rewrite this in an equivalent form. That's 1 over cosine x times sine x over cosine x dx. So that's 1/5. 1 over cosine x is secant x. Sine x over cosine x is tangent x dx. And that's 1/5. The integral of secant x tangent x dx is secant x. And then plus c. This next one, I don't have any rule that tells me how to integrate a multiplication of two functions, nor will we. Like I said, sometimes we'll be going back on the chain rule, in which case that factor is actually the derivative of what the action is on in another part of the function, but that's for another video. Here, when I look at this, I need to remove that multiplication. And I have an exponent of 1, so I'm just going to distribute this cosecant x through. So that's the integral of cosecant x cotangent x minus cosecant squared x dx. And remembering now I can integrate term by term. The integral of cosecant x cotangent x dx is negative cosecant x. Then minus the integral of cosecant squared x is negative cotangent x. And then plus c. So this gives me negative cosecant x plus cotangent x plus c.